Hello, this is Dr. Lukes back to finish up Lab 7. So we discussed this pipe network and the kinds of applications where we might do this. What I want to do next is talk about the equations needed so that you could analyze something like this. So, for instance, in our little lab, what we did is we could measure what is designated here as Q45, the flow rate in this exiting tube, and we could measure that. But can we, based on that, know that there is actually flow going through each of these tubes? And that's really important if you're providing water to, say, a system of homes. You would want to make sure that every every home got water, not just that the water came back out at the end, so it must have been good. It would be terrible if it, bypassed an entire loop here. And so the way we analyze this is actually fairly logical. And the first is doing a balance on nodes. So looking at these split points or mixing points. And at each one of those, we know that the flow coming in is equal to the flow coming out. There is no accumulation at that location. And so that gets us, for our 4 nodes that we have here, we get a system of 4 equations. But we have flow rates in 7 different streams. So that's not enough information yet. But we do know one of those flow rates, Q45 in our case. The last 3 equations we need are going to come from pressure drop. Now, you haven't taken your fluid mechanics in your, now I can't even remember the name of the course, the transport course yet. But basically, what you know is that the pressure at a location is the same in all directions. And so therefore, if I know the pressure here is the same in all of those directions, and the pressure here is the same in all directions, then the pressure drop or pressure change from here to here is the same whether I go along this outer loop path or whether I come across this direction. And so therefore we can add up pressure drops across all the points, and when I get back to this point, if I do pressure drop across here, pressure drop across here, pressure drop across here, when I get back to the beginning, the pressure change should be 0. And so if you go around a loop and add up all of those pieces of pressure drop, you should always add up to 0. And so that's done for our 3 possible loops in this case. Now, pressure drop is related to flow as the square of the flow rate. And there's a coefficient out front, so this equation here, so it's this coefficient out front times the flow rate squared. So therefore, these 3 equations, although they do not look directly like they involve Q, they do involve Q, and we see that it's Q squared. Now, K is going to be a function of that friction factor. So remember Lab 3, we talked about friction factor. This one uses a fanning friction factor. Density of the liquid and pipe parameter, so the length of the pipe, the diameter of the pipe. And if we throw all those things in, we end up with these numbers here. Now you could do this and find the friction factor for our flow rates and using our Q45. Or you can do it from the handout. And the handout has some values that you can use. I think they give you Q01, and they give you a friction factor to use. They tell you lengths of pipes and diameters. And so I really recommend that you do that one. And what you want to do is take this system of 7 equations with 7 unknowns and find the flow rates through each of those pieces. Okay? So this concludes the video portion. Now you need to just solve this problem. Thank you very much for your time.